So let's talk about curvilinear coordinates. I'll start by just talking about the two-dimensional case, which really we either use Cartesian coordinates for the most part, or we do also sometimes like to use polar coordinates, right? So if you pick a point with x coordinate and y coordinates xy, let's say, then you can draw a line out from the origin like so, right? And the length of that r you can define to be r, right? So r in this course will that be the square root of x squared plus y squared. Sometimes in calculus 2 we allow r to be negative, but in here we're going to insist that r is the non-negative. It's greater than or equal to 0. This is called the radius, or perhaps the polar radius. And then of course we also define the standard angle, let's say theta, like so, counterclockwise from the positive x-axis by usual convention. And then standard right triangle trigonometry tells you what? It tells you that the this length right here, or this coordinate more generally, it would be r cosine theta, right? And this one right here would be r sine theta. And it just so happens that the signs, SIGNs of sine and cosine, are constructed so that it's still the case that x is equal to r cosine theta and y is equal to r sine theta, even in the other quadrants where sine and cosine aren't both positive. Like, for example, if theta is between pi over 2 and pi, it happens that cosine is negative, that sine is positive, right? Down here, sine and cosine are both negative. Over here, cosine's positive, but sine is negative. And altogether, what that means is that these formulas, right, are like true for the whole plane, not just where the picture is drawn, right? So if you want to convert a formula from xy to polar coordinates, these are called polar coordinates, you can use these formulas, right? And then, of course, you can also see that there's sometimes nice to know that the tangent of theta we can write as y over x, right? Because the r's cancel. But this is for x not equal to 0, right? And again, I'll just warn you that calculation of the standard angle is a tricky business. In general, you got to really think through it. So those are polar coordinates. All right, that's the one basic thing we should remind ourselves of. Simple example: what to do, what not to do, what to do. Example 1. If I have a circle, x squared plus y squared equal to, say, big R squared. That's the Cartesian form of the circle, whereas, I'm assuming R is positive, okay? Whereas in polar coordinates, that's just R squared equals to big R squared. In other words, in polar coordinates, we just have R equals to R. And so, of course, the polar form of the equation of the circle is more simple than the Cartesian form, right? On the flip side of things, here's what not to do. Well, here's what to try to avoid. If I have a line, y equals mx plus b, that's, usual Cartesian form for a line. If I convert that to polar coordinates, it looks like this, right? So I could solve for r. So apparently r as a function of theta is b over sine theta minus m cosine theta. So in short, the formula for a line in polar coordinates, it's kind of complicated, right? So circles are nice in polar coordinates, lines not so much. Of course, lines from the origin are pretty nice from the origin. Well, not lines so much, but rays are nice. Example 4, how did I get to 4? 3. So like if I do theta equal to pi over 4, that's pretty nice in polar coordinates. I'm not sure I'd want to try to write that. I mean, you could write it in Cartesian coordinates. It'd be y equals x, right? So I guess this thing is sufficiently simple. It's kind of nice in both coordinate systems, right? But pi over 4 is just this ray out to infinity. Okay, that's about all I have to say about polar coordinates for now. We'll come back to them when we're doing integrals a little bit later. Let me move on here. So the two coordinate systems that tend to give people a little bit more trouble, not a lot more, but a little bit more. For one is the cylindrical coordinate systems, right? So cylindrical coordinates, I can't spell today, there's a D there, isn't it? Oh, good grief. Come on. So how do we spell cylinder? So cylindrical coordinates. Now all the spellings seem wrong to me at the moment. Anyway, cylindrical coordinates. So this is one of the coordinate systems for 3 dimensions. And so I'll draw a big picture here. I always try to like connect the coordinate system to the Cartesian. So like the Cartesian coordinate system is kind of our default, but the cylindrical coordinate system we can kind of draw on top of that. If you take a point here, say x comma y comma z, so I'm supposing that like the projection of that point down into the xy plane is like here, all right? So that would be x comma y comma 0. Then the cylindrical coordinates are, well, z is one of the cylindrical coordinates, so that's simple enough, right? But what you do is you draw the line which connects the origin to that point xy0 in the xy plane like that, and then we do what we were doing before, which is namely to define the standard angle to sweep out like this from the positive x-axis. So essentially, cylindrical coordinates say find polar coordinates for x and y and just use z. So cylindrical coordinates are just kind of like, essentially these are polar coordinates and z. Now there's a little bit of fine print there, see, because we're talking about a 3-dimensional coordinate system, so it's not, you need to understand, you take the point, project it into the xy plane, and you find the polar coordinates for this guy. So the formula. So for one thing, this has length r, right? Again, r is equal to the square root of x squared plus y squared. And we still have that right triangle trigonometry down here. So like this guy and this guy make a right triangle in the xy plane. Here you've got your r cosine theta. Over here you've got r sine theta. In other words, we still have x equals to r cosine theta and y equals to r sine theta. And, well, we don't always write this, but z equals to z. I mean, these define the cylindrical coordinates. Here, 0 is less than or equal to theta is less than or equal to 2 pi, by the way. That was also true for polar coordinates, although sometimes we'll use different, we can go from minus pi to pi, or we have other choices there because of the, the degeneracy of the angle. Now, so that's cylindrical coordinates. Now, just one example. Now if I look at the equation r equals to r, it has a different meaning, right? Now it's actually a cylinder. I said one example, I'll give you 2 though. So It's actually a cylinder, right? Centered on the z-axis. So, and radius r, you know? So for one thing, r equals r is a cylinder. This goes on and on. This is just a heuristic picture, but the cylinder keeps going and going and going, right? And then the other example I would mention briefly is just like if you put theta equal to pi over 4, now it's not just a ray, it's actually a half plane. So theta equals to pi over 4. I guess I should have used some color on this one. Whee! So the cylinder is actually just, it's not the solid, right? It's a surface. It's just the collection of points that are distance r from the z-axis. The half plane theta equals pi over 4, well, you go out to pi over 4, like here, right? But the line right above it, and so forth and so on, these are all at pi over 4. So you get this half plane that extends all the way up and all the way down. It goes on and on. But there you go. So that's cylindrical coordinates. And then, of course, the one that's more exciting is spherical coordinates. Spherical coordinates. I can't spell today. Spherical coordinates. What's that look like? Alright, so this one is genuinely three-dimensional. And we do use this a fair amount for integration later. And there's a few more things I'm going to share with you in the notes. I'm just trying to keep it just to the basics here as I'm just introducing the coordinate systems. There, of course, is much more in my notes concerning formulas and details and so forth. But okay, so this is x, this is y, this is the z-axis. I'm also labeling the point x, y, z like that. Again, we can think about, it would be necessary and helpful to think about the projection of that point down onto the z equals 0 or xy plane, right? So the spherical radius is the distance from the origin out to this guy. And in math, we usually use a rho to denote that. So rho, the spherical radius, is the square root of x squared plus y squared plus z squared. That's the distance from the origin out to the point x, y, z. And then we also still use the some of the stuff we did before. Like there's some connection between cylindrical and spherical coordinates in the sense that they both use the angle theta in the same way in this course. So like it's still going to be true that the length of that blue line is r, right? And well, let's see. Here's that. I mean, yes, that's still r, but what's interesting is we introduce a new angle, all right? And that angle sweeps off the z-axis. And so it's annoying, but this is often called the polar angle because it's off the pole. And whereas this is called the Azimuthal angle, which is unfortunate because, this one is like polar coordinates, whereas this one is not. So I'm just going to refer to them by theta and phi. And hopefully the equations will make clear which one. Some people I know also call this the co-latitude because it's like the latitude on the Earth, but it sweeps down from the North Pole instead of up from the equator. But if you look at that, the z-axis and this line are parallel. So by like geometry, these are alternate interior angles to two parallel lines. So that means that this is also phi. And once you know that, then you know that there's a right triangle here, right? And so this gives us z equals to rho cosine phi. And down here we have r is equal to rho sine phi, right? And so we still have, down here, we still have, you know, these things we talked about before. We still have, you know, r cosine theta for x, right? And, you know, we also have, over here, we have y is equal to r sine theta, right? But the new thing is that, I mean, there's a connection between the spherical and the polar radius. The polar radius r is equal to the spherical radius rho times the sine of phi. All right, and so if you plug that into these, we get x equals to rho cosine theta sine phi, y equals to rho sine theta sine phi, and as I mentioned already, z is equal to rho cosine phi. So these, folks, are the fundamental formulas that define the spherical coordinate system. Notice this time that the azimuthal angle theta actually ranges between 2 and pi, whereas the polar angle phi only goes from 0 to pi. And that's because you like sweep down all the way to the minus z axis, but you don't go past it. So the way the angle phi is measured and the way the angle theta is measured is just, they're not the same. That's why they don't both sweep from 0 to 2 pi. Some examples. Example 1, of course, obligatory, rho equals to r. This is a sphere, right, a sphere. The Cartesian equation would be x squared plus y squared plus z squared equals to r squared. I think I'm out of frame here. Sorry about that. Right. Another example, if we have the polar angle fixed at a constant, say pi over 4, that actually gives me a cone, right? In contrast, if I had phi equal to 3 pi over 4, that would give me the same kind of cone, but down here below the xy plane. If I had phi equal to pi over 2, you can plug that into here. What does that give you? It gives you x equals to basically r cosine theta, y equals to r sine theta, and z equals to, what happens when you put pi over 2 into that? You get 0, right? So this gives us z equals to 0. In other words, this is the xy plane. So in between cones which open up and cones which open down, you've got the whole, the cone kind of degenerates to a plane in that in-between case. So, versus in this. I guess I should draw some coordinate systems in here to be clear. This is the z-axis. Here's y, here's x. Z-axis, y, x, z-axis, y, x. We can always compare to the Cartesian coordinate system, you know. Yeah, so that's the basics. Now I have some deeper things in the notes which I'll share with you now. So the notes, I do more. I'll just try to hit the high points here in this video. Obviously, if you want to have more lengthy discussions, you can go back to my lectures from Liberty, where I had 5 days a week, and I talk about this stuff for longer. But our time here is limited, so I'll try to keep it brief. let's see here, as I said, these are the polar coordinates. Let's see here. Here's another picture. These I haven't talked about yet, but r hat and theta hat, these guys are unit vectors which point in the direction of increasing r or increasing theta. So this is a picture. Theta hat is these little unit vectors that encircle, and the r hats just point outward. So we'll use those from time to time. Moving on to cylindrical coordinates, these are the formulas I shared with you before. Here's a picture of the cylindrical coordinates. I think I already drew that essentially. Some kind of here's an example that's kind of nice. Cylindrical coordinates, z equals to 4 minus r squared. What is that? Well, if you convert that to Cartesian coordinates, you get 4 minus x squared minus y squared, which is a downward opening paraboloid. And here I sketched the region that has the cylindrical coordinates bounded by some inequalities. This kind of thinking will be important later when we do integration in cylindrical coordinates, but we'll come back to it then. Here's the cylindrical coordinate frame. It's just the polar frame with z hat tacked onto it. That's the same z hat we already talked about. Here's some pictures of the polar coordinate frame at different points. R hat always points radially away from the z-axis. Theta hat always points in the direction of increasing theta, and z hat points up. The cool thing is that this r theta z forms a right-handed coordinate system, because if you take r hat cross theta hat, you get z hat. If you take z hat cross r hat, you get theta hat. In other words, the cross products of the unit vectors are related to one another in the same way that x hat, y hat, and z hat is. That's what makes it a right-handed coordinate system. I would also point out, if you remember your physics, that these r hat and theta hat are useful. Like if you had a line charge along the z-axis, like if you just had a charge spread out on the z-axis like that, then the electrical field would just point radially out of that. And so here's a formula for the electric field of a line charge on the z-axis. You can use r hat to indicate its direction. If you have a current, I'll draw the z-axis this way this time, just so I can fit it. But if you had a current flowing like that, then the right-hand rule says, like in physics, the right-hand rule, you point your thumb in the direction of current, and your fingers wrap around the wire as the magnetic field lines do. And this is straight up a formula for the magnetic field of a uniform current that's going in the direction of the positive z-axis. So r hat and theta hat are useful for giving nice simple formulas that cleanly communicate the geometry of certain really well-known physical solutions. Here's the way the dot product works. They're orthogonal with one another, and they all have length 1. And as I was just saying, the cross products are related in the natural way. And again, that makes it a right-handed coordinate system. Spherical coordinates. Here's the formulas I derived for you geometrically. Here is another picture of it. Here's maybe a nicer picture of the cone and the half plane. Here I foolishly converted a Cartesian equation of a plane into the corresponding spherical equation of the plane. Obviously, we shouldn't be using spherical coordinates to describe planes because it's horrible. Cylinders can be described in spherical coordinates. They're not too bad, but the equation of a cylinder in spherical coordinates is something like this. If it's a cylinder in the with z-axis as its axis, I suppose. The spherical coordinate frame these are unit vectors which point in the direction of increasing rho, phi, and theta respectively. Theta hat is the same as it was before for the cylindrical frame. Rho hat and phi hat are not, I don't think they're quite obvious. And maybe we'll talk about them more when we use them later, but here they are for your reference. You can derive these formulas geometrically, but I have a way to do it with calculus later in the class. So, you know, whatever. Rho hat's actually kind of easy to understand if you just think about the unit sphere. Like basically if you think about the unit sphere like this, and you take a point on the unit sphere, you know, then the vector which points out to there is rho hat. Like rho hat is the unit vector that points outwards from the unit sphere, but it's also the coordinates of the point on the unit sphere, but the unit sphere has radius 1. So when you put that into, you know, x equals to rho cosine theta sine phi, make sure I'm writing in screen here, I don't know if I am, y equals to rho sine theta sine phi, and z equals to rho cosine phi. If you think about that, when rho equals to 1, it just collapses to cosine sine, sine sine, and cosine phi like that, which is exactly what we have down here for rho hat. So we can kind of see rho hat from just thinking about coordinates on the unit sphere. But phi hat, I will admit freely to you that deriving phi hat geometrically, it does require some thinking. Maybe we'll come back to it later. Here's some pictures of them anyway. So phi hat points in the direction of increasing phi. So it's like pointing downward on the xy plane, because like phi sweeps from the z-axis, so when you get to the xy plane, phi is increasing as you go down. And rho hat just points like radially out from the origin. So for example, if you wanted to write the formula for the electric field of a point charge, which points radially outward from the origin, this is the formula. So like rho hat gives you a nice slick formula for that. You can also write Newton's law of gravitation using rho hat. Again, spherical coordinates are a right-handed coordinate system. They're orthogonal to one another, and their cross products are related in the natural way. But that's why we have to put rho, then phi, then theta. The order matters. If I was to switch the order of theta and phi, then this pattern would be ruined, and it would be a left-handed coordinate system, actually. But anyway. And here I have some more examples, but again, I'll let you, well, let me just look here briefly. So I show you how to get the Cartesian equation for a cone with angle phi equals pi over 3. What you can do is you just plug the angle into the spherical coordinate formulas and do a little algebra, and you can work it out. It's z squared is equal to 3x squared plus 3y squared. And then here I convert this one into spherical coordinates as well. Let me discuss what it means. All right. So, you know, coordinate conversion problems are fun. Oh, this is something to be warned about. In mathematics, we tend to use phi and theta, as I've told you. But in physics, the meaning of phi and theta are exactly opposite, which is unfortunate but true. So like, same letters but opposite meaning. Worse still, if you go into other places of engineering, other people will measure the angle up off the xy plane, like latitude. We do that on Earth, right? Latitude and longitude. So theta is like, our theta is like longitude. Our phi is not latitude. It's related to latitude, but you might call it a co-latitude. I'm just trying to tell you, there are a lot of other flavor choices for how you can set up spherical coordinates, so beware of that. Finally, I should draw your attention to the problems at the end of the chapter. Maybe I haven't spent enough time talking about this, but these are all, solutions to these are provided on my website. And if you look through these problems, I think you'll see that either they're like problems that I've assigned you, or they're awful relevant. So, you know, it would be smart to at least look through these problems, ask yourself for a second, how would I solve that? And then look at the solution which I provided, you know. And I don't think I have everything solved, but you know, there's some of these are bonus. I may not have the solution to this one posted, for example. You know, some of these are pretty good test questions, like problem 17. A dot B equals to A dot C for some vector A. Does it follow that B equals C? Like, if dot products are equal, is there like a cancellation property for dot products? You know, what if it's true for all vectors A? Then can you cancel and get the B equals C? So I think problem 17, 18, 19, and 20 are really great test questions. But anyway, I will shut up. I will point you to these problems are worth looking at. There's probably one or two of them that are in your homework even. Goodness gracious, look at that. Problem 29 is so much like. Oh, actually, it's a dot product. It's not a cross product. I thought that was like your homework. It's actually a little bit different. Well, anyway, I will shut up, and I think we'll start up next on what's the next topic here. Well, I'll find out soon.